We are now on record. So, this weird phenomenon again. Let me just do that again. Just here. All right. Okay. So this week's examples covering some of the topics similar to the exercises we have and similar to the ones that we mentioned during the lectures. Here's the first one. So we have it's more of a warm-up in some sense of the sort of thing that we want to discuss with the testing. So it's just got an example which leads to us making a conclusion about the same kind of conclusion that we make when we do a statistical test. So it's also meant to give you a rudimentary understanding about the nature of the statistical test and why it's a bit different than just one sample. So it's just, you know, you can't test whether the expected value of the, let's say, rolling a die is in fact 3.5 by just simply rolling it once. That's not how it works. So anyone who's played, for instance, games of chance where there's let's say you roll 2 dice. So on average, if you roll 2 dice, then you get a 7. But, you know, sometimes you get snake eyes, sometimes you get 12, right? So it's not so that the expected value can be just deduced from one roll. But if you make it many times over, then you are bound to get closer to the expected value. And if you make many enough of them and you still don't get close to the expected value that you thought was the expected value, then you may conclude that the expected value is not what you thought. So here we have a idea that there's a lamp and it has a lifetime in hours of X, which is a random variable with an expected value 1,500 hours and a variance of 200 to the power of 2. So that would be 40,000. The variance would be 40,000, but you know the standard deviation is 200 hours. So the question first is that what is the probability that one lamp lasts for 1,430 hours? So let's first look at this one by one. So when we have a normally distributed variable, then the way you do it is you calculate this. So if you have let's say you have the sigma, so standard deviation equals sigma, right? If your standard deviation is sigma, and in this case, it's 200 because it's the square root of the variance. And the normal, when your expected value is mu, in this case 1,500, and the way you can refer this to with the software or using a table. If you have any normal distribution, then you can normalize it to the 0-1 normalized distribution by taking x minus mu divided by sigma. So that's your z, right? Then that will be 0-1 normally distributed. That's one of the basic things about the normal distribution, one that we rehearsed in the previous weeks, but I want you to understand that this is all the tests are based on this idea. So if you know the standard deviation, which is the square root of the variance, and you know the expected value, then you can transform the variable into a 0, 1 normal distributed variable. And the 0, 1 normal distributed variable has it's easy to handle with the software or looking from the table. So in this case, our result is 1,430 hours. So if we do this, calculate this Z from here, so that would be the result minus mu. In this case, it's that would be 70 over 200, and then what you get is minus 70 over 200, so that's minus 0.35. So let me just draw a picture here. So we transform, so we you know, this subtract the mu, translates the expected value to 0, and divide by sigma, compresses it or elongates it depending on what the sigma was into the 0, 1, you know, so that the variance becomes 1. And now we get a value which is minus 0.35. Maybe it's a value somewhere in here. So the question is, what is the probability that one lamp lasts for sorry, 1,430 hours? So, I mean, the wording of this question is a little bit vague. What does it mean? Lasts for 1,430 hours. Is that long or longer? So I interpret, yeah, exactly. It should say at least, yeah. Well, it doesn't matter. If it's at least, then we interpret it as if it's at least, then we interpret it as this probability. If it's at most, then we interpret it at this probability. But the thing is, if it says exactly 1430, then the probability is, of course, 0 or almost 0. Well, it's very small. You can think of that if it's within 1 hour of that. That's. But it should say at least. Yeah. Yeah. Exactly. So the reason being here, I'm going to do this. So if I use the norm CDF, I get the probability of this, and that's the at most. And then if I want the at least, then it's 1 minus that. It's all this probability. So, you know, it starts somewhere. 0 would be somewhere pretty far away in here. It can have a negative lifespan. So the assumption that it's 0, 1, well, it's normally distributed is broken a little bit if you have very, very small values, but never mind that. So this probability here is all the values smaller than 1430, or in this case, when I normalized, smaller than minus 0.35. And then 1 minus norm CDF gives me this region here. This is the probability that one lamp lasts for 1430 hours or longer. The probability that it breaks down before then is, of course, then 0.3632. So the thing is, we got a 36% chance that it breaks before this time, and we got a 67-ish percent probability that it breaks down. It lasts at least this long. Well, let's say that this calculated a test where we take 100 lamps and sample mean is a random value. So we should determine a C such that the probability that X is smaller than or equal to C is 0.01. Again, it's best to use the standardized sample, you know, this normal 0, 1 normal distribution. Remember that if you have the sample mean, then the sample mean is normal distribution with the expected value that is of the original, but the variance is divided by n. And then that's 200 to the power of 2 divided by n. So the standard deviation is the square root of that. So the standard deviation of the sample mean is 200 over the square root of n. So this is simply taking the standardized sample mean, which would have 0, 1 normal distribution. And here we have n equal 100. So that's 200 over the square root of n is just 20. It's 200 over 10. We have this 0, 1 normal distribution. So we have this probability that if we subtract 1500 and divide by 200 over n, which is the square root of n, which is 20, so we get that this is smaller than or equal to z is the same probability that z is smaller than or equal to c minus 1500 and over 20, and that should be 0.01. So here we can look from the cumulative normal distribution, what is the value where this is 0.01? And we can use the norm inv, or we can look it up from the table. If you have a table which doesn't have this 0.01 probability, it only has those probabilities that are higher, you can look at the 0.99 probability and then take 1 minus that. Sorry, take the negative of that. Sorry, not 1 minus, the negative of that, because it's it's the symmetric situation. So if your table only contains these positive values, then you can take the 99, which conforms to the 1% chance, and then just take the negative of that because it's symmetric. But using norm inv, you get that that's the inverse of the cumulative distribution function, because this is what the cumulative distribution function should be, 0.01. So you get that the cumulative distribution function, sorry, at this point should be 0.01. So you take the inverse, it should be the cumulative distribution function at minus 2.3263, and then this is the value at which it is, so it's c minus 1500 over 20. So we solve this for c. So multiply by 20, add 1500, so we get 1453. So this is the value. So if we take 100 lambs, then the probability that their average lifespan is less than or equal to this is 1%. So we did the test and we got the average at 1430. Do we still conclude that the expected value is 1500 hours? Now the question here is, this is simply a statistical test, just like we had. So the answer to this question depends, of course, on the risk level. The risk level being the risk of you being wrong, in the sense that it actually is 1500, but you deduce that it's not. And in this case, we said that we can set the risk level to, let's say, 0.01. Then clearly this risk level means that if we get any value under 1453.5, then we conclude, that with risk level, well, something less than 0.01, we can reject the null hypothesis. So it's probably lower. So, if this result seems improbable under the assumption that the expected value is in fact 1500. We can calculate other risk levels. We can calculate, if we want to calculate the actual p-value of this, we can calculate the p-value by doing it the inverse again. But we'll be calculating p-values in many situations later on, so I'm not going to go through that. You normalize the 1300 here. In fact, you can normalize this and get, we can do this. Let me just start off with It's not. So we can calculate the p-value of this. So if you're looking at the paper, I can't share both at the same time, or I don't know how to share both at the same time. So we want the p-value. So we will calculate the normalized version of this. So we had, remember that our let's say our n is now 100, right? Our sigma is 200, and our x bar is 1430, right? So we can calculate the z at sorry, our mu. I'll just do, I like to do it this way so that you understand what the values are that I'm using. I can just, let me just elongate this. Oh, sorry, I'll just make this a little bit bigger. All right, so we have these values now. These are from the example numbers. So 1430 is our x bar, and that's our mu. So we can calculate the z at, that would be x bar minus mu over the, well, sigma divided by the square root of n. So we get minus 3.5. Well, that's what you would get if you look at the numbers, and we were 100, so we're dividing by 10. So you know, the divisor there is was 200. In this case, it's 20. So with the 200, we got minus 3.5 and sorry, minus 0.35. So this should be 10 times more. So okay, then we look at the cumulative distribution function at z, and we get a very small value. That's 2.3 times 10 to the minus 4. So that would be 2.3 in 10,000. So that's 0.0002326. Yeah. So the p-value here is very small. So this would be your probability. If you reject now the idea that 1500 is the expected value, then even if it is, then this is the probability of getting a result this small if it were 1500. So you can't really assess the probability that you are wrong. This is the probability that this is the probability that this is what you get even though it's right. So, but when this is very small, we have a smaller probability of having making this mistake. So yeah. So the ex ante, the before the test probability of rejecting it, that's why we use the risk level. I mean, we can just calculate the p-value, of course, and say that, okay, if we chose the risk level to be this, then with it, because this p-value is smaller than that, then we would have accepted it. And that's how it's often done. But you know, purely in a purely scientific way, if you think about it in a way that scientists should think, that the ideal is often that we we set our standards beforehand, and then we make a test and see what happens. And in this case, if we had set the risk level to 0.1, then what we got was something that is definitely smaller than the threshold for that risk level. So yeah, we reject the null hypothesis. We don't no longer consider the expected value to be 1500 if our risk level is 0.01 or greater, or if, you know, in retrospect, if it's greater than 2 point something out of 10,000. All right, so let's move on to the next question. So we have a certain measurement which is normally distributed, and this is the thing. This is like a warning example. We are going to do a statistical test with a very small n. So there are 3 caveats here that need to be understood. First, in this case, n is very small, and we'll see that that has a huge effect on what we do here. So what will happen is we will get a result that is very close to being interpreted in one way and another. Intuition here breaks down. Second, it's imperative in this case to understand that we assume that the measurement is normally distributed. In this case, the n is so small that if it's not normally distributed, then all bets are off, really. And the third one is that we see that the risk level here is somewhat arbitrary, and, you know, again, referring to the first point, it's somewhat how should I say? It's somewhat arbitrary setting the risk level and somewhat counterintuitive in this case. So let's see this. So here we have 3 measurements. We get 25, 28, 28. So the expected measurement should be 30, not under. We have a normally distributed variable, but we don't know anything about the expected value other than the null hypothesis being 30, and we don't know the variance. So the thing is, variance could be far greater than what we're dealing with here. I mean, we calculate a sample variance here, and because we're calculating the sample variance, in this case it would be 3. So we can calculate this with the, for instance, with MATLAB or anything. You can use the mean. So you could. I'm not going to do this with MATLAB because it's so simple. But mean x would be, and var x, where x is this 25, 28, 28. So this is really, these are really the things that you need to do. So we can calculate this sample average, the sample mean. In this case, it's 27. The sample variance in this case is 3, and we have a 3 as our n. So the t, we use the t statistics here because this is the t distribution. So that it differs from the normal distribution in that this is a t distribution with degrees of freedom being equal to 2. That's n minus 1. And here we are dividing it with n, which is 3. This is the sample variance because we don't know the variance, and we take the square root of it. Well, that's just 1. We get minus 3. So we can calculate this t inverse 0.052. We get the risk level being at minus 29, minus 2.92, and t is t alpha. T is smaller than this t alpha because we get something. The critical region starts at minus 2.92. So anything below that, again, I mean, I'm going to use this picture, the same picture. The t distribution with n equal 2 is far flatter than this, but you get my idea. So I calculate the t in of I calculate the t in of 0.05. So let's say the 0.05 probability is here. If it falls in this region, then it's in the critical region, and it falls just next to this line here because it's just below this. If you calculate the p-value, you can do this with the TCDF. The TCDF command calculates the p-value. So you would calculate this as TCDF minus 3 and 2, right? So you'd get 0.0477. So if the risk level was a little bit smaller than this, then the null hypothesis would not be rejected. So the point here is that, okay, understand this. With small n, you shouldn't do this statistical testing unless you are 100% rock solid sure that your values are normally distributed. If they're not, then this result is pretty nonsensical. I mean, it doesn't say much. It could be, it could not. Maybe, maybe not. I mean, let me just say, let's say that you have a random experiment that results with the expected value is 30, yes. But it gets 3 different values, 25, 28, and 50. The 50 is very rare, but it happens just so often that it offsets it and makes the expected value into 30. You make these 3 measurements and you come up with a p-value. It's very small probability that this is the expected value is under 30. Sorry, that is not under 30. So that is 30 and not under. But it is. It could even be much higher. Maybe you get 1 in 10 measurement gives you 1,000. So the expected value would be like 120 something. But you know, you conclude that it's not that big a deal. So here's the understanding that you need to come up with, is that this hinges absolutely on the idea that it's normally distributed. And with this small an n, this result would be completely nonsensical if it's not normally distributed. Okay, and it's a bit counterintuitive. I mean, think about it, 25, 28, 28. I mean, all right, we got these results. I'm going to conclude that it's under 30. I mean, we got 3 results. Everything is under 30. So it's pretty unlikely that we get something greater than 30. I mean, if you think about it, if the expected value is 30, what is the probability of all these results coming in at under 30? I mean, even let's say it's not normally distributed. It's uniform distributed with some range that I don't know, an expected value of 30. In that case, I would conclude that, okay, what is the probability of getting this result? So it's a 50-50 of being under 30. So that would be 0.5 times 0.5 times 0.5. That would be 0.25 times 5 is 0.125. So that's about 12% chance. So you see here that this test statistics means nothing if your measurement is not normally distributed. That's very important to understand. With this small an n, this test statistics means nothing unless you are absolutely sure that it's normally distributed. All right, let's carry on. So we have 1 kilogram or 1,000 gram packages, and they're being filled with 2 machines, A and B. Both machines produce 12 packages. We pick them up and we weigh them. And the results that we get is that the average weight for machine A is 1,076.75 with sample variance of 29.30. And the expected value for B, the sample mean for B is 1,072.33 with a sample mean of, sample variance of 26.24. Now, we assume the weight is normally distributed in both machines and they have equal but unknown variances. And remember that I said in the lectures, you can't this kind of question where you have two samples with differing variances, sample variances, and differing expected values, you have to make assumptions. If you can't assume that the variances are the same, or if you can't assume that you know each of the variances separately, then it's very hard to come up with meaningful test statistics for this. So assuming that the variances are the same, we can test whether the machines produce Békéssis with the same expected weight. So let's calculate the p-value and do both one-tailed and two-tailed tests. This is highly important. So first we calculate the sample joint sample variance. What is this joint sample variance? Why does it look like this? Why does it look like this? Well, it looks like this because, you know, look, here are, I already drew this. So here are the sample variances of both X and Y, right? So how do you reconcile this with what is going on is that you calculate the weighted average. Sorry, that should be squared. You have to calculate the weighted average as though, you know, you were having these measurements and these measurements, and then dividing it with the degrees of freedom of the whole thing. So here, this is gained from that sum by dividing with 11, which is n minus 1. So this is the raw sum of all those squares of differences from the expected value. This is the raw sum of all those squares of not expected value, but sample mean, of the sample mean in B. All right, these are the raw sums of those. But remember that in each of these sums, the average in this is calculated from the sample, and the average in this is calculated from the sample. So there's really the degrees of freedom there, because the sample average is fixed, so it depends on all of those 12 points. So if you fix one of them, then you know. Sorry, if you fix 11 of them, then you will know what the 12th one is, because you know their average, right? So you add these together, and then you divide it by 22, so which is 11 plus 11. You divide this, so this is the weighted average of, in some sense, it's the weighted average of the sample variances. And what we get here is 27.77. So, you know, it's, in this case, it's actually, I mean, if you really see the ends are the same, then it's really the average of these. Honestly, I mean, if you think about it, if you have the same n here and the same n there, then what happens is, then this is simply the actual average of these two. But this is like the weighted average of these depending on the sample size, right? See, it's not that hard. 27.77, so it's the average of these. Now, this is the sample variance that we're going to be using. It's calculated from a sample of 24 with degrees of freedom 22, because we had two different sample means that were used. A null hypothesis here is that the expected values are the same. So in a one-tailed test, so it says do both one-tailed and two-tailed test. In one-tailed test, the alternative hypothesis here would be that because mu a, this average seems a bit higher than this, then in a one-tailed test, we test that whether this in fact is greater, the expected value is greater. So the way we do it, we calculate the test statistics, and it's the same in both cases. We calculate the difference of these sample means, and we divide it by the square root of, but here, we use the sample variance from this plus the sample variance from the sample variance divided by NA plus the sample variance divided by NB. So there was a little bit of a jump in the lecture material on how this was derived. It turns out that this will be a t-distributed variable. I'm not going to go in great detail here on how it was derived. You can look at the derivation from the material, but we skipped the derivation just a little bit. It's just simple algebra, really. This is a t-distribution with the degrees of freedom equal to, well, n minus 1 plus m minus 1. So in this case, it's 22, so it's 11 plus 11. So we get the t value for this to calculate simply from this, and we could punch in those numbers into MATLAB. I'll shortly do this. So we get the value of 2.0545. So let me just punch in these numbers into MATLAB and be done with that. Oh, it's not okay. Just 1 second. Normally I would have two big screens that I could do this with, but in here it's. So I'm going to just call it XA at 1076.75, XB at 1072.33. So I have S2A at this is getting really frustrating with this when this is so small. This S2A at 29.30 and S2B at 26.24. Okay, here are my starting numbers now. So I calculate the fixed S2 at, so my NA is 12 and B is 12, right? So I calculate the S2 at, so it's NA minus 1 times S2A, then plus NB minus 1 times S2B divided by NA minus 1 plus NB minus 1. Okay, and I get this 27.77. And now my T statistic in this case is XA minus XB divided by the square root of S2 divided by NA plus S2 divided by NB. And I get this too. This is my T, this is my test statistics. Now, I want the one-tailed test. So I'm going to calculate this. This is my T distribution. So I'll just show this. So my T distribution is here. I want this value. This is my, well, that could be my T statistics. And what I want is, I want to find the T alpha, really. And if my one-tailed test, then I want the T alpha such that this region here contains 5% of the probability. And the way I do it is I calculate that T alpha, I'm going to just call it TA, at T inverse of 0.95 with the degrees of freedom is now NA plus N. So this NA minus, well, it's just 22. I'm not going to go, it's 22. It's NA plus minus 1 plus NB minus 1, but it's 22 side. So this is my alpha. And if I get my test statistics is greater than this, so it's in the critical region. So in this case, I reject the hypothesis that the expected values are the same, and I accept the probability, the alternative hypothesis that A has a higher expected value. So we already have the T statistics. So now we need to calculate, let's calculate the two-tailed test. We have the test statistics, but in the two-tailed test, it's a little bit different because you have to understand that the upper echelon has to have the half of the probability and the lower part has to have half of the probability. So why would we choose two-tailed test? Is that here's one important thing to understand. You should choose the test that you are going to make before you look at the data. In this case, we looked at the data and we noticed that this A had a higher expected value. And then we concluded that we make the one-tailed test. But the one-tailed test is really for a situation where you have a prior reason to believe that A has a higher expected value. Because then, you have some prior reason to believe that, and that's why you discount the probabilities that are associated with the smaller values. But if you don't know that A has a higher probability of, for some reason, it's the alternative hypothesis is formulated as A has a higher expected value, it's that it could be higher or it could be lower. And we are accepting a 95%, a 5% chance of being wrong or getting the wrong result, really, getting the kind of sample that gives us the wrong result. And where are those probabilities? They are at the lower end and the upper end. And because we are equally likely to believe that it's high or it's low, then we calculate the upper at having T up. Let's call it T up as T in that my critical region starts not at 0.5 but 0.75, because that's 2.5% chance. 2.5% chance of being higher than this, and T up and T down, and I get here 0.025. That's 2.5% chance of being lower than this. So my critical region, of course, these are positive and negative of the same value, because if it's negative this, so if it's below this T down or above this T up, then we reject the null hypothesis. But in this case, we notice that my test statistics is in fact between these T up and T down. So we don't reject the null hypothesis. Let's go back to the question and see what's going on. So we can calculate the p-value. I didn't calculate the p-value yet, so let me just go back. Let me go back there. Let's calculate the p-value in each of these cases. So what is I have my t here. The t is this. So what is the p-value of this in the one-tailed test? In the one-tailed test, it's simply TCDF, T, 22. And then because it's in the higher region, then it's 1 minus this, right? So that's your 2.6%. This p-value is 0.026. But remember, what is the p-value when we are doing the two-tailed test? The p-value in the two-tailed test is the minimum of the upper and the lower times 2. Times 2 because we have the two-tailed test. So this is my p-value in the second case. So that's 0.052. That's above alpha. So this begs the question, why on earth do these give the different result in this? Can anyone explain why do we get the different result from the two-tailed test and the one-tailed test? Does it matter, or is it completely nonsensical? What's going on? Can you think? Please think for yourself a little while. Just think. I'm going to give you a couple of minutes to think. Because the thing is, the thing about this question is that maybe I'm not sure what you mean by test larger. This is a non-trivial question for me to even answer. I mean, what is going on here? So think about it. In the one-tailed test, you have the whole probability mass. Let's say we are assuming that it's a t distribution, or it could be the normal distribution, whatever the distribution of your test statistics. In the one-tailed test, you are only picking the largest 5%. In the two-tailed test, you're picking the 5% that is on the edges of the region. So it's the 2.5% at the left-hand side and 2.5% at the right-hand side. So the critical region is the same size in both, but the other one has half of it at the lower echelons and the half of it at the upper, and the one-tailed test has all of the probability mass at the higher. So the reason here is that, I mean, philosophically, this is a hard question to answer. Why would we make this conclusion in any different way? And it's a valid question here to ask whether it makes any sense to use the two-tailed test, you know, if you want your hypothesis to pass your test, or whether it makes any sense to use the one-tailed test if you want your null hypothesis to stand, because then it has a higher probability. That's a valid question, really. But usually I like to frame this in a way that I say that, okay, if you use the one-tailed test, then you have a prior reason to believe one is greater than the other. So you don't need quite as hard evidence to say that it is larger. You're willing to accept that. But really, I mean, it's just as improbable, because in the previous, in the two-tailed test, you know, you still have a 5% chance of, in both cases, you have the 5% chance of rejecting the null hypothesis. The important thing to understand here is that you should set your test standards before the fact, before you calculate your test statistics. You should set your test statistics before that. Sorry, test standards before that, because of course you can move the goalposts. Whenever you get some value, you can move your, okay, this is what I wanted and this is what I got. Alternatively, you can interpret it in such a way that the statistical testing is a bit of a nonsensical procedure. Some people are of this opinion, honestly. My personal opinion is that I'm a bit undecided in the grander scheme of things, but I would like to say that this is a valid idea. You set the standards. When does my data pass the test? When do we get a null hypothesis accepted? When do we reject it? And we decide this before we know what the values look like. So here, one way to see this is that I don't look at these numbers. I set the standards before I look at them. and then I'm shown these numbers. Of course, because if you don't have no reason to believe that, if you believe that these are just random numbers and these could be larger or smaller, this could be larger or smaller, then 5% chance of rejecting should include the smaller and the higher values. Now the question really is the risk level? That's a good question. How do you justify the selection if you write a scientific paper? That's a good, yeah. Are the customs based on a field of study? That is exactly what is going on. And the thing is that it is customary nowadays to just give the p-value of the result and be done with that. Very often the people give the p-value and then it's left for the reader to decide whether that's meaningful to them. But honestly, it's a very field specific thing. So there are people who say, if it passes the 5% chance, then it's statistically significant. If it passes the 0.01, so 1% risk level, then it's highly significant. And if it passes the 0.1%, then it's extremely significant or something like this. So there are different standards for that. Really, honestly, there is no applies everywhere kind of standards in this case. I've seen a lot of arguments. You can look it up over the internet. There's a lot of arguments whether or not you should use the risk level at all, because the risk level is when you read a scientific paper, you cannot know whether they opted first to set the risk level and then collected the data, or whether they looked at the data and then just said, okay, we'll use this risk level because that's how we get meaningful results, right? So there is no way to see that from yeah, that's superficial. It seems a bit superficial to reject a hypothesis based on a preset value. You can say that, but then again, you can say that if you set your standards beforehand, then your conclusions are not open to what's that word? Second guessing after the fact. So the idea of setting the standard, the preset value before you draw the conclusion, say that if I get a p-value of smaller than, or if I get a value greater than this, and these are my critical regions, if I am going to get a value that is in here, I'm going to move on and reject the null hypothesis. If I don't get something, then I'm going to have to work with the null hypothesis or do further studies or something like this. You have to, if you set that standard before you make the decision, then at least you're guaranteeing to yourself that you're being honest. Because if you just collect the data and then you see that, okay, I got this result, I'm going to work with this result. And okay, those of you who are not, I'm guessing not many of you are, but people who are hardcore Bayesian, they reject this idea completely. They reject this idea completely because this idea is based on this is based very heavily on the frequentist idea, so that if you carry out many tests, then the numbers will converge to the expected values and so forth. So this is all very, very tied to the frequentist idea of doing this. And even the whole idea of the alpha or the risk level or the p-value is that if I set my alpha to 0.05 and I set the risk level like this, then 5 times out of 100 tests will give me the wrong result. So I'm going to do this now. I'm willing to go with this hypothesis if it's if I get one of those results. But then there are fields of study that do meta-analysis. So they do meta-analysis, and what meta-analysis means is that you collect all those papers that talk about this topic, and then you gather the results, and then you conclude with a smaller alpha usually that okay, this seems like, you know, this is statistically significant. This is much more significant because there are 12 studies that were done. 11 of them found statistical significant result and one didn't. So you can fix the significance level there and so forth. But honestly, there are sociological ideas in science that go against this. This is all based on an ideal that people, when they conduct a study, they will publish it. The problem is, of course, that when people conduct a study, then when the null hypothesis is not rejected, then it is very common that the paper is not accepted when you submit it to a journal. So, you know, if you look at the papers that were published, most papers that were published were papers that ended up rejecting the null hypothesis, and that applies to almost all fields. The thing is, if you reject the null hypothesis, I mean, if you only accept papers that reject the null hypothesis, you're contaminating the data. You're contaminating the whole scientific procedure. If you are to trust this, you see what I'm saying? So, dog bites man is not news. Man bites dog is news. So. You will have more news headlines saying man bites dogs than dog bites man, whereas the case where dog bites man is very much more common. And if you just read the news, you would believe that it's men biting dogs, but not dogs biting men. So the same applies for science as well. Null hypothesis rejected is publication. Null hypothesis not rejected is a rejected paper. So there's a risk involved in interpreting scientific literature, and especially for the high alpha results and p-values that are relatively high. I'm digressing here, so let's move on. This is just as a sideline. When I said I don't want to teach this course previously, I said to my superiors that you know, I'd rather not teach this course. The reason for this is that this is the sort of thing and thinking that needs to be taught with this statistical testing, and we don't have the time to really tackle this issue in this course. But be understanding of that. Conclude this exercise 3. So you mean, what is the conclusion? So what we got here okay, yeah, let's conclude this. So this exercise 3, what we got here was that if we use the one-tailed test, we come up with the result that A is in fact has a larger expected value than B. And it turned out that it's with p-value about 0. I didn't calculate, 0.026. The reason is that we had all the probability mass of the possibility of rejecting all the probability was here. But in the two-tailed test, only half the probability is here. The other half would be in this. So because it's in the critical regions, it's just narrowly in the critical region. Here it's narrowly out of the critical region if we have the two-tailed test. So we get a different result. So the conclusion is that the one-tailed test adds evidence in a different way. So the alpha should be, you know, the risk level should be interpreted a little bit differently in the one-tailed test from the two-tailed test. And if you have no previous preconception about the values, then you should use the two-tailed test. That's the conclusion here. The two-tailed test is more robust in some sense. Let's go to number 4. So we have a random variable that has a normal distribution with unknown variance and unknown expected value. The sample of 10 items has the sample variance that is approximately half of the, sorry, it has a known variance. It has to have a known variance. So we get a sample variance that is half the actual variance. Is this unusually small? Test with risk level alpha equal 0.1. So what is going on here? So we have a known variance of sigma. We don't know, we use this symbolically. So think that this known standard deviation sigma it's some value, but we don't know what it is. And the sample variance is something that we got. We know what it is, but it's immaterial what it is, as long as it's just 1/2 of the actual variance. And is this a really small variance or a really big variance? When n equals 10. Test with risk level alpha 0.1. Would we reject the null hypothesis with a 10% chance? So the test statistics for this we need the test type. Sorry, there's a little bit of a weird wording here. So we need a test statistic for testing the null hypothesis that, yeah, it is the original. So we got this s squared is roughly equal to the variance divided by 2. So concomitantly, the variance is 2 times the sample variance. This is my null hypothesis now. An alternative hypothesis is that, in fact, the actual variance is smaller. So we have a one-tailed test again. And in this case, we are going to use the chi-squared distribution because that's how it plays out. So here's my chi-squared distribution, and I'm looking at these values here. So forget the fact that there's a high tail, there's a low tail, one-tail test, and we're looking at these. So 10% chance of being here, and the other is, does it fall into this region? So we're willing to, this alpha being 0.1, is we're willing to really reject the null hypothesis pretty easily even. So we calculate the test statistics. It's the familiar where we have the s squared times n minus 1 divided by sigma squared. And this should be chi-squared distributed with n minus 1 decrease of freedom. In this case, we get 10 minus 1, that's our n, so that's 9 times s squared divided by 2 times s squared, because here that's our variance in the null hypothesis. So we divide it by 2 squared. So we get 4.5. And we can calculate the p-value directly, because we can just calculate the p-value of this. What is the probability of getting something smaller than or equal to 4.5? So we look at it up from the chi-squared cumulative distribution function at 4.5, and we get a p-value of 12%, but just over 12%, just under 12.5%. So because this p is greater than 0.1, this is not at all that unusual. The critical region would be anything below 4.16282. We can calculate it by using the chi-squared int 0.19. So we see that this is not in the critical region. So what's going on here? What's going on here? What's going on here is that if we have a sample of 10, then the sample variance in more cases than 1 in 10, the sample variance is in 12.5% of the cases. the sample variance can be off by a factor of 2. You know, it can be too small by a factor of 2. So we conduct, let's say we conduct 10 studies. No, let's say we conduct 20 studies with 10 samples. Then 20 studies. So we get about 5 of those. Just under 4 or 5 of those studies will have a sample variance that is less than half the actual sample, the actual variance. We can calculate also what it is if it's twice that. So if we have the divisor at 1/2, so that would be 9. What would be 18? So if we calculate that, just very quickly, I'll do that with, so we can do it with the G squared CDF at 4 times that, that's would be 18, 18 and 9. Yeah, well, we get about 4% chance of it being 2 times too large. So 4% plus 12%, that would be 12 or 4, 3, 5, that's 15. Yeah, it's over 15%, 16%. So if we conduct 20 studies, then more than 3 of them will have a large or small. Yeah, so it's a very high chance of getting very small values for the sample variance and pretty big probability, not quite as big a probability of getting double, 2 times as too large. So you see what the problem here is, that you see here already that the variance in the variance, if you take the sample variance, then the scope of what you might get from the sample variance is actually pretty large. This should justify the idea that the t distribution is a much flatter distribution, because the sample variance has a lot of uncertainty to it. All right. All right, any questions regarding this one? You should be able to conduct this. I'm going to give, next week, I'm going to make those tables which have these test statistics, and the only thing you have to understand is when do you use the test statistics and so forth. I'm going to draw one sheet. Probably the exam will even be such that you have or use all the materials. So I'm probably going to do it. So I've already looked up some. So probably the idea is that there is a workshop that will open, or something like this, that will open at a certain time. You can do the exercise. You have 3 hours to look. You have your questions. You have 3 hours. Then you submit, and then you submit your answers electronically, and then I will verify them later on and give you grades based on that. So in that, you have at your disposal all the material that you can come up with from the internet or from whatever. But it's just a few hours, so you have to be versed enough and practiced enough to be able to carry out these computations. Let's move along. Here's number 5. 2 liquid dispensers, A and B, are examined for difference in variance. So, in fact, the variance test for differences in variance is, in fact, very much easy. The statistics is notoriously easy. because the test statistics is simply the proportion of the variances, and it follows the F distribution. In this case, we have two different size samples. We have 21 bottles for machine A and 26 bottles for machine machine B, and they have sample deviations of 0.8 and 0.838 and 0.573. We assume normal distribution here. Again, normal distribution needs to be assumed if n is, well, if n is relatively small. Here 21, 26, that's still quite small. So if it's any other distribution, you have a high risk of getting wrong results. We assume the amount of liquid dispensed is normally distributed. It has a normal distribution. Test with risk level alpha 0.05 whether the variances are the same. All right, I'm going to switch to the MATLAB now. So I have these questions parameters here. So I'm going to write here that SSA is S2A. So I'm just going to make, so it's, sorry, I had SA. SA as equal to 0.838. I have SB at 0.573. So I am going to calculate the test statistics for this. And the test statistic is simply one divided by another. But remember, these are standard deviations. These are sample deviations, not sample variances. My F statistics will be SA squared divided by SB squared. And that's my F statistics. I get 2.1388. And now the degrees of freedom are 20 and 29. I want the critical region. I want to find the critical region, and I have the F distribution. So if I have 5% chance, then F inv, and I want the lower region 0.025, and I need the two parameters. And in this case, the A, I have to, the one that is divided, that's A, and I had NA equal to 21. So I have N minus 1, that's 20. And then the one that divides, the one below the line, that's the second parameter, its N is 26. So I use here 26 minus 1, so that's 25. So that's my F low. I write it like this. So this is my lower, and anything below this would mean that B, we conclude that B has a greater variance, and F high 0.975. Anything higher than this, we would conclude that that A has a higher variance. And it seems as though our F statistic is below, it's between these values. It's below that F high. So we conclude that we do not reject the null hypothesis here. We do not reject the null hypothesis here because we got a value that is higher. Okay. Sorry, the value that is between, not higher. It's not higher than the upper limit, and it's not lower than the lower limit. So we conclude that yes, they might as well be the same. that's the way we. Oh, I used 26 there, not 27. Ah, there's a. So if I used. Oh, it seems like in my paper answer I had a slight error there. 26. I used 26 instead of 25. I have punched in the wrong numbers beforehand. Sorry about that. Because NB is 26, so I should use here 25 instead of 26. So let me just go back to the, my MATLAB was correct. I'm going to have to fix this model answer. You see what I did here? Sorry. I made a small error in here. It doesn't change the conclusion. Just a second. Doesn't change the conclusion here. The conclusion is correct. But you see here I had a mistake. That's 26 instead of 25, which it should be. So I made a small blunder here. What happens? What happens in the F? I mean, here's a one thing, whether you've understood how these distributions work and how this F statistics would work. So what do you think would happen to the critical region limits if we had a higher N? What do you think happens? If I have a larger sample size, if my NA or NB is larger, then what do you think should happen to this F distribution? You know, what do you think would happen to this this critical region here? Any thoughts? Yeah. Why? Why? That it's true. The critical region becomes smaller if my N. No, sorry. No. The critical region. Remember, that's the far ends of that. So let me draw a picture. So the F distribution also looks a little bit like this, right? The F distribution also looks a little bit like this. So the critical region is these regions here. So the critical, let's look at that. Let's look at that. Look, my critical region is things above F low and things, things below F. So I have higher F high and F low. So if I calculate this F high and I put here, that's 2.3005 with 20 and 25. If I put here 40 and 50, then what happens to this value is it becomes smaller. So the critical region increases, because the thing is, why is this so? Like, can you think about why this is so? Well, what happens to this S squared A and S squared B? What happens to those values when I increase N? What happens? When I take a larger and larger sample, what happens to the sample variance? What does the sample variance become when I take a large, when N approaches infinity? No. It's really important to understand that no, that's not what happens. It doesn't grow. In fact, it converges towards the actual variance. So when you have a sample variance, then the sample variance is a shape parameter of the distribution. So for instance, if we have a normal distribution, then the variance of the normal distribution is a number. The sample variance is a random variable. And when we make a measurement of the sample variance, then we get some number. Let's say that this here, just left hand, these are the values. On this direction, we get different random values. If my n is small, I get all kinds of these values here for my sample variance. This is the real variance. If my n grows larger, they tend to cluster closer and closer to this value. If n grows to infinity, I get something that is yes, that is true. The bigger the n, the easier it is to reject the null hypothesis. That is exactly what happens if the null hypothesis is false. So, if the null hypothesis is true, then the bigger n you get, the lower chance you have of rejecting the null hypothesis. That's wrong. If the null hypothesis is true and you have a prefixed alpha, if you set the alpha to, let's say, 0.05, when you increase the n, the probability of rejecting the null hypothesis will approach 0.05. If the null hypothesis is true. If the null hypothesis is false, then the probability of rejecting, yes, we are talking about these both. So type 1 error probability is and always remains at alpha. Type 1 error probability always is alpha. If you choose alpha beforehand, then it's alpha. That's type 1 error, the error that if H0 is true, you reject it. The probability of type 2 error, meaning that H2 is false, but you accept it. That should become smaller and smaller as n grows. So, when n increases and we maintain type 1 error as fixed, then type 2 error probability goes down. And in that sense, it's easier to reject the null hypothesis with larger n. This is a very deep question for you to ponder and understand how the nature of this. Why we want to gather more and more data, it is that for a given alpha, the probability of getting the true answer, if you will, reject or accept, that's our decision. Reject the null hypothesis, which is like, we accept the alternative hypothesis, or accept. And if you given alpha, it means that if you have a given alpha, then the probability of rejecting the null hypothesis approaches that alpha, if the null hypothesis is true. If the null hypothesis is false, then the probability of rejecting the null hypothesis approaches 1. The probability of rejecting approaches 1 if it's false. So, to answer your question, the bigger the n is, the easier it is to reject the null hypothesis if it is false. So that's why when you have a large n, then you can have a smaller alpha as well. But really, really very often what happens is when you have a very large n, then the p-values tend to be very, 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 very small. When you test something that actually you know to be true, you can try this out, you can test something you actually know to be true. When you have a very large n, then your p-values may be, they're zero within margin of the accuracy of your computing equipment. for very large n. For instance, you can try this. Test the make a random generator give you 1 million die rolls, n equal 1 million. Assume the die roll has normal distribution with the original parameters. Calculate the average and test for the hypothesis that the average is greater than 2. And what you will get is a p-value that it's 0. You will reject the null hypothesis that the expected value is 2. Or even that the expected value is 3. If you throw the dice 1 million times, then the expected that average will be so close to 3.5 that you don't have even, I mean, the computing equipment's accuracy won't matter if you have a good random number generator. Yeah, that's really important to understand the differences between the type 2 and type 1 errors here. Yeah, larger n is better in every way. All right. Any other questions? All right. I think we're going to conclude this session shortly now, if there are no other questions. We'll reconvene on Monday at 2 p.m. Talk about this on Monday at 2 p.m. We still have these exercises. So I hope you will be able to muster those exercises. I'll make the additional exercise session available next week. And next week I'll also figure out the details of the exam. All right. I'm going to stop now and see you guys on Monday.